So we're going to start talking about projections and some applications of the dot product. And where we're going to start is we're going to start with these things called direction angles. So a direction angle, very simply put, is basically it's the angle that's created between a vector, okay, a single line vector, and the coordinate axes, okay. So like let's say for example we imagine I've got this vector here that goes out in space, okay, and what I want to do is I want to know one of its direction angles happens to be here. That's the direction angle with the vector j, okay, because that's the y-axis. I might also want to know, like, if I imagine this vector and I've kind of got like there's an angle that comes out here on the x-axis, right? So I've got my x-axis here, or a plane that's kind of parallel to the x-axis, and I want to know, well, what's the angle that I'm getting there, okay? And I may also want to know, say for example, what that angle is right there. Okay, call it theta 3. Let's make this theta 2 and theta 1. All right. And so we might want to know actually what each one of those angles actually is. It might come in handy in terms of like kind of breaking down a vector into its component parts. It might come in handy inside of like later applications, and it will. Okay. And so to find that angle, what we're going to be doing is we're going to like let v be a vector in 3 space, and we're going to just dot it. So v dotted with I, okay, v dotted with j, and v dotted with k. And just kind of to give you a sense, j here is the y-axis written as a vector. So that's the y-axis written as a vector. If we think about I here that's the x-axis, okay, right? And remember, this is 0, 1, 0, and this is 1, 0, 0, okay? And it's the x-axis. And then we have the z-axis, okay, ends up being k, and that's the vector 0, 0, 1. So essentially, we're going to use what we learned about finding angles using the dot product and the understanding that each one of these axes is, in fact, a vector of some sort. We can represent it as a vector, okay? And so these are all 3 of these. These are direction angle, or these will help us to find. They help define the direction angle, okay? V dot I, V dot J, V dot K. So let's take a look at an example. Let's suppose that we have v equal to 2, negative 1, 1. And we want to find the direction angle and the direction cosines for each axis. So remember, what we're going to use is we're going to use that cosine, or that theta, okay, equals cosine inverse of, and it'll be u dotted with v divided by the magnitude of v times the magnitude of u. Okay? And so what we're going to be doing, since we're finding the direction angles, we're going to be finding v, okay, dot I, v dot j, v dot k in each case. And we'll also need to know, right, because those are going to be our u's and our v's, okay, x-axis, y-axis, z-axis, okay. So if we start out with v dot I, and then we're also going to need to figure out what the magnitudes are. Now, quick thing, I, j, and k, they're all standard unit. Okay, they're all standard unit vectors, and you can go in and actually find the magnitude of each one of them. But because they're standard unit vectors, they each have a length of 1. Each one of those has a length of 1, so it's actually quite simple to figure out. Okay, and then the magnitude of our v in this case is going to equal the square root of 2 squared plus negative 1 squared plus 1 squared. Okay, and so that's the square root of 6, and that's the magnitude of v. Okay, now let's take a look at something. When we try and find v dot I, v dot j, and v dot k, what happens? So I take v, all right, or I've got 2, negative 1, 1, and let's dot it now with I, which is 1, 0, 0. So I take I, I'm going to dot it with 1, 0, 0. And what you want to notice is that, well, I'm going to take 2 times 1, that's 2, okay? But then I've got negative 1 times 0 and 1 times 0, so I'm just going to add zeros each time. So this ends up equaling 2, all right? And that's v dot I. By the way, this is always going to be the case no matter which vector you use. If you dot v with the vector I, for example, all you're going to get back is just the single component, in this case, the x component. We'll see that what happens with the v dot j is just going to give us a y component, so it'll be negative 1. So we got v dot j, which equals negative 1. Okay, and you can go through and actually check that by taking that dot product. And then we'll take v dot k, and that's going to end up equaling, k, is going to end up equaling 1. Okay? So now we'll find our direction cosines. So cosine of theta for v dot I, cosine of theta is going to end up equaling, it'll be just, we've got 2 divided by the magnitudes. So we got these magnitudes, v and u, and so that's 1 times the square root of 6. So that's going to equal 2 over root 6. For v dot j, it's going to be negative 1 divided by, and it'll be 1 again, because remember it's a unit vector, times, okay, the square root of 6, because again that's the magnitude of v, square root of 6. And then v dot k is going to equal 1 divided by the square root of 6. And there we go. Or excuse me, cosine theta, in both of these cases it's cosine theta, my bad. Cosine theta, and again this is for j and this is for k. So our cosines are going to equal this, right? 2 over root 6, negative 1 over root 6, and 1 over root 6, okay? So if we think about this for direction angles, we can kind of, we can simplify this process. So if we are looking at the direction angle with I, notice that it's just going to end up equaling, it'll be v1 divided by the magnitude of v. v1, not v to the first power, but v1 divided by the magnitude of v. For j, we're going to get v2, the second component, divided by the magnitude of v again. And for k, okay, this is not equal to, just say that they're going to relate to this, we're going to get v3 divided by the magnitude of v again. And those are going to give us our direction cosines. Excuse me, direction cosines. So our direction angles then are going to look like this. Theta, right, for my I, theta is going to equal cosine inverse of, in our particular example, 2 over the square root of 6. For j, we're going to get theta is going to equal cosine inverse of negative 1 over the square root of 6. And for k, we're going to get theta is going to equal cosine inverse of 1 over the square root of 6. Go put those into your calculator and you actually end up with the direction angles, right? And our direction cosines. So basically what we've done here is we kind of pulled the angle out of the vector, each component angle out of the vector, okay? If you remember in two directions, right, it's pretty simple. You've just got, you can just choose the x or the y. You can kind of just use a little bit of trig, which ends up giving you the same thing, okay? But in three directions, we've got to actually kind of pare down or remove pieces of information, like the x information and the y information, to get our z information, and this is basically how we're going to go do it, okay? So that's finding direction cosines and direction angles. So what we're going to do now is we're going to talk a bit about projections, and projections are just really crucial doing any kind of application, any kind of like applied mathematics. You're going to utilize projections a lot. And what we're going to look at here is we're going to look at the basics of projections, and it all comes from vector calculus. So here's the idea of a projection. Let's imagine that I have a vector u. Okay, so here's my vector u, and I have another vector v that starts at the same exact spot. So it has the same initial point as u. what I can do is I can actually draw a line down to U and create an orthogonal line with U, basically creating a right triangle. So I've got this right triangle here, okay? And there's some information that we have here because it's a right triangle, all right? One is this line here now. This, the horizontal, although it's not horizontal, basically the line that's running along U, okay, or this, the vector that runs along U, we're going to give it a name. And it's called the projection of V onto U, okay? So onto U, right? And we're projecting, this is the vector that gets projected. So that's the vector that gets projected. All right? And how we say that is that this is the projection of V onto U. Okay? Now, what we want to do is we want to figure out actually what that projection is. So, like, we want to ask the question, how do I find the projection of V onto U? All right? So the first thing that I'm going to notice, I'm going to draw this. I'm just going to draw it flat ways. And, you know, here's U. I'm just going to imagine that U continues on, but I'm not really interested in the remaining part of U. I'm only interested in this piece right here. Okay? I'm interested in that piece right there. And so what we want to notice is that this is a vector. This vector is projection of V in the direction of U is in the direction of U. Okay, so it actually is in the direction of U. And if you remember from 2.1, we actually found those vectors. We found a projection of V, we found vectors, right, that were in the same direction. And how do we do it? What we did was we found the unit vector, okay, and we then multiplied it by some scalar, right? Multiplied it actually by the length of whatever it is that we wanted, the magnitude of whatever it was that we wanted, okay? So first, we need a unit vector in the direction of U, okay? So we want a unit vector in the direction of U, and so what that vector is, okay, is going to be U, the vector U, divided by its magnitude. Remember, that's how we actually transform a vector into a unit vector. So now this is the unit vector. Now what I need to do next is I need to actually go in and figure out how long is the projection of U, or the projection of V onto U. How long is it? Then I'm just going to multiply that by the unit vector. Okay? So again, I'll draw my triangle again, all right? And it's a right triangle, and remember, here's the magnitude, there's V, okay, there's the vector V, all right? And if you kind of think about this, you really actually don't have to think about this. Here's theta, by the way, okay? The magnitude of V, right, okay, times cosine theta is actually going to end up equaling that distance. So it's going to be equal to the magnitude of the projection of V onto U. Okay, that's that length. Basically, like, there's your radius. You multiply that by cosine theta, and what do you get? You get actually the length of, like, the horizontal part of this triangle. So that's actually your magnitude. So we're going to do a little bit of work with this magnitude right here. Okay, we're going to take this. We've got V cosine theta, and what you want to remember is that U dotted with V is going to equal the magnitude of U times the magnitude of V cosine theta. Okay? And now, if I go in here, what I can do is I can just actually divide through by the magnitude of U onto both sides, and I get U dotted with V divided by the magnitude of U is equal to V cosine theta. And so here is what V cosine theta equals. V cosine theta is going to end up equaling U dotted with V divided by the magnitude of U. So that is the magnitude of the projection of V onto U, right? Okay, could have actually just shorthanded that. So the projection of v, the actual vector, right, which is what this is, okay, is going to equal its length, which is u dotted with v, divided by the magnitude of u, times, and then it'll just be multiplied by this vector. So it's going to be u divided by the magnitude of u. So it's going to be u dot v divided by the magnitude of u squared times, and this is times, by the way, not dotted, I should say. We'll make it sure that it's multiplication multiplied by u. Okay? This ends up being a scalar, right? It's kind of like the length in the direction of u. And that actually is our vector u. And that actually gives us how we actually go out and calculate our projection. Okay? The idea here is this, is I've got a vector, the vector v, okay? I'm going to squeeze it down onto u, all right? And basically create its horizontal piece with relation to u, right? Like that part that's going along with u, all right? And then I'm utilizing some trigonometry, essentially recognizing that I form a right triangle. The u portion, or the magnitude of that length, is going to be given by the magnitude of v times the cosine of theta. That's that length, right? Just using some trig, okay? And then we'll multiply that by the unit vector in the direction of u, which is found by u divided by the magnitude of u. So this ends up giving me the equation for the projection. And there it is. All right, so now let's take a look at some projections and find some projections. So we want to find the projection of v onto u. And remember that's proj u, right, v. And so we'll let v, we'll start out a, we'll let v equal 351. And we'll let u equal -2, 4, 3. And so we want to remember, okay, remember I'm going to write it out here for you. You'll write it down yourself, okay, that the projection is going to be u dotted with v divided by the magnitude of u squared times the vector u, okay? So what I'll do first is I'll find u dot v. So u dot v is going to equal, it'll be -6 plus 20 plus 3, which equals 17. Then I'm going to need to find the magnitude of u squared. So the magnitude of u squared, right, is basically just each component squared. So it's going to be -2 squared plus 4 squared plus 3 squared. Just in case you forgot, remember the magnitude's a direction, or is the distance, right? It's the length of the figure. So it's the square root of each one squared, each component squared. But if you square it, then you take off the square root. That's kind of the idea that we've got going on here. So now this is going to end up equaling 4 plus 16 plus 9, and so that's going to end up being 29. Okay? So that means that we have 17 over 29, and we'll multiply that by the vector -2, 4, 3. Multiplying those two together, I get the vector -34 over 29, 68 over 29, and 51 over 29. And that is the projection of v onto u. And that's it. That's basically how I think about it. When I'm doing it, I'm like, okay, well, I'm going to do each component part, right? I'll find the magnitude of u. I will figure out what u dot v is, right? And then I will basically plug those into my formula and figure out what that is. And then we're all done. Let's do another one. Let's do b, okay? And we'll let v equal, and we'll have this be 3i minus 2j, okay? And we'll let u equal I plus 4j, okay? And now these are two-dimensional, so this is 2D. We don't have to do 3 of them, okay? They just have an I and a j, so we can assume they're two-dimensional. Basically, I could transform these into components if I want to, or I can just work with them as standard unit form. Okay, create a little distance there. So we'll start out with u dot v. So u dot v, remember, is going to be 3 times 1, okay, because those are the components, plus negative 2 times 4, and so that gives me 5, okay, or excuse me, negative 5, negative 5. And then the magnitude of u squared is going to equal 1 squared plus 4 squared, which equals 17. So by projection, I'm going to multiply that by u. The projection of v onto u is going to end up equaling, and we'll just make this will be negative 5 over 17 times I plus 4j. And so hence it'll be negative 5 over 17i minus 20 over 17j. And that, in fact, is the projection of u onto v if we were doing it in our standard unit form. Now what I want to do is I want to do something called resolving a vector into its component parts. So we said, okay, you can imagine that a vector gets broken up, like we've got u, the vector of u, and we've got the vector v, okay? And here's u, all right? And when we want to resolve a vector in its component parts, we basically want to create two orthogonal vectors, all right? Two perpendicular vectors, one of which that's in the same direction as as u, and the other one which is orthogonal to u, all right? And both of them, when we add them together, right, we get v. So the idea here is that we want one vector. We'll call this one vector the projection of v onto u, okay? That's one of the vectors we want. We want a second vector, which is orthogonal to the projection of u onto v, okay? And we'll call this one, by the way, we'll call this one, we'll call it q, all right? And we'll call this one p, right, just for the sake of our conversation. And then the third piece is we want that q plus p should equal v. So when we add the two orthogonal vectors together, what we get is we actually get v. So basically, right, like their sum ends up giving me the entirety of v. All right? So if I think about that, what's going to happen, I'll squeeze my u down, okay? By the way, this is what we want. I've got v here. Let's imagine I've got v. Here's u, okay? I'm going to project v downward, and so this line here, that's the projection of u onto v, okay? And then here, this thing right there, that's going to be the vector, which is orthogonal, okay? That's going to be our vector p, okay? So that's how that's going to work, all right? And you know what? Let's actually switch these out. We're going to make the projection, we're going to call the projection p, and we're going to call the other vector q, p for projection, q for something else. Okay, so there's q. Now, it's actually pretty easy. Once I know what the projection of u onto v is, okay, and by the way, here's v, then q is just v minus p, right? Okay, if you kind of think about it, that's how we find geometrically, that's subtraction, is you basically are just going to connect, right, the two vectors, okay? Because that projection ends where the right angle begins, right? And then we have v. So q ends up equaling v minus p. Q is going to be v minus p, okay? And that's our connection. And so there we are. I mean, like, that's it. You find the projection, and then you take your original vector v, you subtract the projection, okay? So we call this v minus the projection of u onto v, okay? And that gives us our orthogonal vector, and then we have resolved our components. Okay, let's take a look at an example like this, and we'll actually show that this is in fact exactly what's going to happen. All right, so let's take a look at an example. Let's suppose that we have two vectors. I've got v equal to 5i minus j, and I have u equal to 4i plus 2j. Right, so those are my two vectors. And what I want to do is I want to find, or I want to basically construct two vectors, two orthogonal vectors, whose sum is v, and where one is the projection of u into v, okay, And there it is. So construct two orthogonal vectors whose sum is v and where one is the projection of u into v. All right? So the first thing that I need to do is I need to find the projection of u into v. All right? So we want to remember that projection of u into v is going to equal u dotted with v divided by the magnitude of u squared times u. So I'll do just a little scratch work. I've got u dotted with v, or actually, why don't we do this? We'll take u dotted with v. So that's 4 times 5, so that's 20. Okay, plus negative 2. And then we'll divide that by the magnitude of u squared. So the magnitude of u squared is going to be 4 squared plus 2 squared. Okay, and then we'll multiply that by 4i plus 2j. 4i plus 2j. And so what we get is we get 18 divided by 20. Okay, 18 divided by 20 times 4i plus 2j. And that is 9/10 times 4i plus 2j. And that then is going to end up being 36 over 10. Or actually, we can do this a little bit more. Okay, 18 over 5i plus, and this will be 45, not 45, excuse me, 9 over 5j. And that is our projection. There's our projection, and there's that. Now, remember that the orthogonal vector that we're looking for, okay, that vector q is just going to equal v minus p, or the projection. Okay, so it's going to equal 5i minus j, okay, minus 18 over 5i plus 9 over 5j. So that's going to end up being 25i minus 18 over 5i, that's 7/5 I. And then we'll get 5 over 5j minus 9 over 5j, so that's minus 14 over 5j. And there is q. So our two vectors, p and q, so we've got p, the first vector, is 18 over 5i plus 9 over 5j. And our second vector q is equal to 7/5 I minus 14/5 j. Okay? So we'll first figure out what p plus q is. If we've done our job correctly, this should equal v. So this is going to be 18 over 5 plus 7 over 5. So 18 over 5 plus 7 over 5i plus, and this will be now 9 over 5 minus 14 over 5j, which equals 5i minus j. That looks familiar. Oh, that's v. 5i minus j is v. So consequently, they add to v. Okay, this equals v. Check. Correct. Okay. Second thing, I want to know, what is p dot q? Since they're supposed to be orthogonal, p dot q should equal 0. So let's see if that's the case. I take 18 over 5i plus 9 over 5j, and I'm going to dot that with 7 over 5i minus 14 over 5j. And what do I get? That ends up equaling, all right, we've got 18 over 5 times 7 over 5 minus 9 over 5 times 14 over 5. Go ahead and do the math. That's 0. Okay? They've got all the same factors. I mean, that's got to equal 0. Okay? So check, right? We got p plus q equals v, like we wanted, and p dot q is equal to 0. So what we've done, or excuse me, equal to 0, not 0 vector, but 0. Okay? And so consequently what we've done is we've resolved the vector v into two orthogonal parts, one of which is in the same direction as u. Right? Long way to say that kind of thing, but that's basically all we're doing. All right? So how do we go about doing that, or what's the method here? What we'll do first is we'll first find the projection of u onto v. That's what we did here first, okay? Then I've just got to go in and I subtract that projection, okay? That's the projection right here. P is the projection, and I'm going to subtract that from V, and that gives me my Q. And then this last part is just a check. It's a check to make sure, okay, that we got what we intended. That they both add up to V, and in fact, that they are orthogonal. Now let's look at some applications of the dot product. Let's start out with some basic applications that have to do with, we'll call them economic, although really we might call them practical, real world, real life. You're going to see these in a lot of different places, especially if, say, for example, you're a computer programmer, because this kind of stuff, the dot product is really useful for doing these kinds of things. So let's suppose that the child has 25 Yu-Gi-Oh cards, 32 Magic the Gathering cards, and 52 Pokemon cards. According to a card collecting website, Yu-Gi-Oh cards are worth, on average, 26 cents, Magic cards are worth 31 cents, and Pokemon cards are worth 43 cents. How much are the child's cards worth? Now, you know how to do this, right? You're going to take how much each card is worth, you multiply it by the number of cards, blah, 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 done. But what if, say, for example, you wanted to write a computer program that did this and would allow you to change how much the Yu-Gi-Oh cards might be worth, how much the Magic cards are worth, how many of them you had, okay? So what we can do is we can actually generate we can turn these into vectors. So we'll have our first vector, we'll call our first vector V, and it's going to equal, okay, the number of Yu-Gi-Oh. That's going to be the first component. The second one is going to be the number of Magic cards. And the third component is going to be the number of Pokemon cards. And so that's going to be V. Conversely, we can generate another vector called U, and U is then going to be the cost for each one of them. Okay, so basically we're going to be the number vector, and then we'll have a cost vector, something along those lines. And so this is cost of Yu-Gi-Oh, call it Y. Then we have the cost of Magic, cost of M, and then we have the cost of the Pokemon cards. Okay, and you might assign some variables in there, whatever. What you want to notice is that if you take v.u or u.v, it doesn't really matter, okay, that's going to equal your total. It's going to end up equaling your total. So you can ascribe, you can construct a vector that's made up of each number of cards, and then in the same location or the same spot, you'll put the cost of the same kind of cards, okay? And then when you dot the two together, it'll give you your total. So this ends up equaling, right, okay, if we think about our total for in our case, we got 25, 32, 52. We'll dot that with 0.26, 0.31, and 0.43, okay? And then when you do the dot product there, you should see that it's 25 times 0.26 plus 0.31, or excuse me, plus 32 times 0.31 plus 52 times 0.43. Kind of convince yourself that in fact that's going to give you your total cost. And so when I actually do my calculations, I get that I got a total of $38.78. And so what we've done is we've kind of created a program that will allow us to figure out the cost of all these different cards. The cool thing about this is something like this, you can construct vectors that are very, very large, right? Like you can have hundreds, thousands, tens of thousands, sometimes millions of different variables that you're looking at, and you just describe them with, call it V, call it U, call it whatever it is that you want. Some things that I've seen this used for is like, for example, pixelation, right? So like the number of pixels within particular squares that kind of tells you what a picture actually is. It's one of the ways that we end up being able to do artificial intelligence. So it's like a really kind of cool application where these vectors kind of come into play. All right, let's look at a physics problem. And we're going to use the dot product here and some of the work that we've been doing with projections. So let's suppose that a ship is traveling 20 degrees north of east. And it travels at a speed of 20 knots along this path. Okay, so we've got the ship. So here's our origin. It's moving 20 degrees. Here's 20 degrees. Okay, here's directly east. And there's 20 degrees north of east. And then the magnitude of that, okay, the magnitude, we'll call this vector V, is going to equal my 20 knots. Okay, that's going to end up being the magnitude. Then we get an ocean current, and the ocean current is going to be going at 45 degrees. Okay, so it's going to be moving at this 45 degree angle. Okay, and its magnitude, we'll make it a little bit longer. Okay, the magnitude of what we call U is equal to 4 knots, right? So speeds are registered in terms of magnitudes. They're the magnitudes of our vectors, okay? And then this angle here, all right, is going to end up being 45 degrees. Okay, call that maybe theta 2. Now what we want to know is we want to know how fast is the ship, which is traveling along this line, right? I'll make it another color so we can see it very clearly. Along this yellow line. How fast is it traveling in that direction if we factor in the current, okay? So essentially what we're going to be doing is we're going to be taking this magnitude, the magnitude of 20, and we've got to add to it whatever piece that we get from U, from our current vector, okay? And this vector right here, that vector is going to end up being the projection, okay, of U onto V in this case, right? V was our original vector, so projection of U onto V, right? If we want to switch it around, maybe we want to make the original vector U, and that way we can just use our original equations, the U there, and we're going to make this one V. And then we can change this, the projection of V onto U, right? That's going to be what that vector actually is, and its magnitude is going to be the excess speed from the current. So basically it's the amount of the current speed that it's going to be pushing it in the direction of the container ship. Okay? So what do we have to do, right? We're going to have to go figure out what that magnitude is. But that's not so bad. That's basically going to be U dotted with V, okay, divided by the absolute value of U. And that's the magnitude, right? That's going to be our magnitude. If you remember, we found that before. Magnitude of the projection of, switch those around, projection of V onto U. Okay? So first, U, we already know that U, the magnitude of U is 20, so that's going to be 20. And then now we just need to figure out what U dot V is. Okay? Well, it's not all that bad, okay? If you think about it, here's what's going to happen, okay? This angle right there, that's the angle between U and V, all right? That's our theta. If we imagine I've got, here's V, here's U, here's theta. And if you remember, or if you remember from one of the things we did earlier, U dotted with V is going to equal the magnitude of V times the magnitude of U times cosine theta. Right? We have that equation. We found it earlier on when we were working with dot products. So this, the U dot V, okay, is going to equal, well, the magnitude of V is 4 times the magnitude of U is 20, and then the theta is the difference between this 20 degree angle and the 45 degree angle. Okay? So basically in this case it's going to be cosine of 45 minus 20. So it's 4 times 20 times the cosine of 25 degrees. What do I get? I get 72.504, so we'll just make it 72.5 if we round to 2 decimal places. And that ends up equaling the magnitude of that projection. All I got to do now with that, okay, so I take this, I'm going to divide it by 20, and I'm going to add that to the 20 knots that it's already traveling. So the total knots here, okay, this is how fast the ship is going in the direction of V based upon the current. That's the addition that we're getting from the current. So my total knots is going to be 20, that's from the ship, plus 3.625, okay, or 23.625 knots, and that's how fast it's going in that direction. Now, it's also getting a push upward, so it's kind of like moving, it's veering a little bit because that current is pushing the ship a little bit in a particular direction, so it's probably got to, move itself down. but just from the perspective of just the component moving in that 20 degree direction, okay, that is going to end up being 23.625 knots. All right, so let's suppose that we've got the same container ship and it's traveling 20 degrees northeast at a speed of 20 knots, but the current is going to move at the speed of 2 knots and it's going to go 45 degrees southeast. So now the current's going in a different direction. How fast is the container ship moving in the direction 20 degrees northeast, by the way, northeast, factoring in the current? Okay, so now I'm imagining again, here's my container ship. It's got this magnitude. We're going to call this guy, it's U. All right, because that's the direction that we want to move in. So remember, U is always going to be that thing that we're going to project onto. All right, it's going to be the vector that we're projecting onto. And so that's going to equal 20 knots. And then I've got V. So there's my axis. And then I've got V, and V here, it's got a magnitude of 2, and it's moving 45 degrees southeast. Okay? So what I'm going to need to do, I'm going to still need to be able to do things, but what I'm going to really got to do is I've kind of got to flip this around. Okay? I've got to flip this around in order to draw that triangle to help myself envision what exactly is going on. So I'm going to pull, I've got 20 degrees on the bottom, or 20, it's the length here, that's the magnitude of U, is equal to 20. Then I've got my V, my magnitude of V is equal to 2 now. And now this angle right here, theta, that's still equal to 65. And so this is just helping me to kind of envision what's going on here. And I'm going to project V onto U, just like I was doing before. So I'm going to project V down onto U, just like I was going to do before. And so consequently, that magnitude that I'm looking for there, because I'm just going to add the two magnitudes together, the projection of V onto U is going to equal U dotted with V divided by the magnitude of U divided by the magnitude of U. Remember, U dot V is going to end up equaling the magnitude of U times the magnitude of V cosine theta. And then we'll divide that through by the magnitude of U. So that actually means that we're going to get this is going to be the magnitude of V cosine theta. That actually might be even easier for us. So that's going to be 2 times, and this is cosine of 65. So there's our magnitude, and our magnitude ends up equaling, or the magnitude of this projection, excuse me, is going to end up equaling 0.8452. Okay? So in order to figure out how fast is it going in that singular direction, we'll add the two magnitudes together. We've got U, the original movement of the ship. So we've got 20 plus 0.8452, which equals 20.8452 knots. And that's how fast it is going now in that 20 degree direction. Okay? So basically, like, what we're doing here is we're utilizing this projection, or utilizing the idea of a projection in order to figure out how fast something is moving. Like we might think about wind speeds. Wind speeds could do the same thing as we could do here with like the speed of the current. You've got a plane moving in a particular direction. You've got a wind speed that comes in at another angle, okay? And you want to know, well, how does that change the plane moving in the particular direction that it wants to go in, right? Is it it'll make it faster going in the direction that it wants, or slower, depending upon if it's a headwind or a tailwind. And then in addition to that, it's going to move it off of its axis, or move it off of its bearing a little bit, because, you know, basically you can imagine the wind moving it, kind of the wind moving it perpendicular, right? Kind of pushing the angle off a little bit, okay? And that's essentially what we're going to be doing for things like this. Now let's take a look at work. Let's suppose that we have a child, and the child is pulling a wagon with a handle at an angle of 45 degrees with a force of 10 pounds. And the child pulls the wagon 100 feet. What is the work that is done by the child in pulling the wagon? So there's a couple of things that we want to get. We want to get one, that our work, okay, our work essentially is going to equal, right, the force generated times displacement. So it's going to be force times displacement. All right. And so we're imagining the force. We've got this wagon. Okay. Got this wagon. all right? And it's got this handle at a 45-degree angle. And we're going to pull it. The displacement here is going to be 100 feet. So that's how far actually it's going to be pulled. And the force that's being exerted on the handle is 10 pounds. So the magnitude of this force vector, call it V, is going to end up equaling 10 pounds. Or actually, we'll call it F. Okay? And there's that. Okay? So the thing about this is that if I figure out the force in the direction of the wagon, okay, and I multiply that by the displacement, what I end up getting is I actually end up getting the amount of work that's being done by the child in moving the wagon. So let's think through this problem. We're going to think through some of the physics, and then I'm going to kind of simplify it for the how do I do it kind of thing. So I've got this force vector, okay, F, and then I've got basically, we might think of it as the x-axis, okay? In fact, you definitely think of it as the x-axis. And so what we want to get here is that this x-axis, right, the 100 feet is not actually the vector that we're looking at. I just want to get that this is I, right, that vector I, and so it's got 1, 0, right? That's basically, that's going to be the vector. If it's in three-dimensional space, it'd be 1, 0, 0, right? Okay, but it's just got that x component, okay? Just the single x component. And so it's flat along the ground, and so consequently, this angle right here is in fact 45 degrees. We already knew that, okay? And what I'm going to do is I'm going to imagine that I've just got, I'm going to project. I'm going to project F, okay, onto I, right? So essentially, if I wrote this as the projection onto I of F. Okay, so that's the projection of I onto F. And we actually know what this is already, okay? And that's because basically if the force vector, we got F here, okay, then the length or the magnitude of this projection is just going to end up equaling the magnitude of F cosine of theta. Okay, the magnitude of F cosine of theta, and that's because basically we're just finding out what that length is. Okay, so what this is this is the force generated in the direction the wagon is moving. Okay, and then the displacement is essentially how far did it travel. So there it is. How far did it travel? We actually can call this, we'll call this length, or this vector, we'll call it PQ. That's the one that your book uses. So there's my vector PQ. Okay, and so I'm going to move the wagon 100 feet. So the displacement is, I've got that vector PQ is equal to 100. That's how far it traveled. Okay, and the force that's being exerted on it, okay, in the direction of the traveling, right, force in traveling, is equal to the magnitude of the force times the cosine of the angle between where the wagon is moving and the handle is. That's it, okay? So this ends up being, so our work, which is force times displacement, is going to end up equaling the magnitude of PQ, or how far the thing's traveled, times the magnitude of the force times the cosine of the angle between the, in this case, the handle and the movement of the wagon, right? And in other words, that's 100 times 10 times cosine 45, okay? And so that is 1,000 times root 2 over 2, which is 500 root 2. And that's the work, okay, that is done by the wagon. Now, this actually is, if you kind of look at it, what you're going to notice is you're going to notice that what we see here is we see an equation again, right? So this is just, we'll put a little recall here. I'm going to bring it up again. U dot V equals the magnitude of U dotted with, times the magnitude of V times cosine theta. So if you look here, this work, which is the magnitude of the vector PQ times the magnitude of the force vector times the cosine of theta, that's U times V. So basically, we can also rewrite work to equal the displacement vector, whatever that is, dotted with the force vector. And that ends up being our work. So let's take a look at another example. Same example, different cases, different system of measurement. We'll use metric this time. So we've got a car is towed using a force of 1,600 newtons, and the rope to pull the car makes an angle of 25 degrees with the horizontal. Find the work done in towing the car 2 kilometers. Now, my work, all right, a joule, 1 joule, all right, which is our unit of measure when we're working in metric, is going to be 1 Newton times the number of meters. So we're going to actually have to write this in terms of meters, okay? So we'll imagine I'm going to move the car 2 kilometers, all right, which is actually equal to 2,000 meters. 2,000 meters. And then you got, here's your car, and here's your tow truck, all right? And there's a line, okay? There's the line. The angle created with that line, okay, is theta equal to 25 degrees. And the force, right, the force that's being exerted, so if we imagine that this thing here is in fact V equals 1,600 newtons. So that's the force generated by the line. So my work done is going to end up equaling, well, this is really actually kind of simple, is 2,000, that's the displacement, 2,000 meters times 1,600 newtons, that's the force, times the cosine of 25. Times the cosine of 25. So we go in, we put that into our calculator, and we get 2,900,184.919 joules. Sweet. There it is. Look at that. Not so bad at all. Okay. One thing to notice, I think that might come in kind of handy a little bit later, is to remember also that work is the displacement vector times the force vector. So some problems are actually going to be written in terms of, I've got one vector called the displacement vector, how far it traveled, right, and what direction it traveled. Then I have another vector called the force vector. And then all you're going to do to find work there is you just dot the two of them. Find their dot product. Okay? There we go. So that gives us the last application that we're going to be looking at for this part of the dot product. We'll have more applications for the dot product later on. Okay? So what we did here today inside of this video is we went in, we looked at projections, we looked at direction angles and direction cosines, okay? And then we looked at some applications of of the dot product, in particular focusing in on the applications of projections. Those projections come up all over the place. You're going to see them quite a lot. So kind of get comfortable with them. Okay.